come.
Where did it go? Oh my goodness. Gotcha.
Okay. Hello, Eric.
Hello. Ooh, ooh.
Okay, let's sit down. Sit down. Hello.
Ooh.
Hello. Ryan, you want to come?
No.
Okay. Eric.
Yes.
So today we're going to talk about the important, the most known sorting algorithm, which is called QuickSort.
Algorithm.
Yeah, QuickSort. So can you tell me what it does? QuickSort.
I heard you say about QuickSort.
Yeah. Yeah. What does it mean? I mean, QuickSort. Sit down.
It means, I think it means sorting
Sorting.
quickly.
Sorting quickly. Exactly. So
See? Big ring.
look. If you given the number,
Ah.
Eric,
Where did it go?
if it's 2, 1, 6, 5. So after quick sorting, what do you think you will get?
I'm a four-headed monster.
Huh? What do you think you will get? Please, Eric, listen. Okay.
1, 2, 5, 6.
1, 2, 5, 6. Okay.
No
So-
big brain here.
Okay. So that's the sorting algorithm. Okay. So how do we this quick sort? How does it work? I mean, look, if you're given a like 2, 5, 6,
7, 9.
6, 3. Okay. Maybe one more number. 1. Okay. So first of all, how it works is that we need to pick a number. This number can be any number, random number, or the first number, or you can pick the middle number, or you pick the last number, any number. Okay, so can you pick a number? Just any number. 2, right? Okay, 2. So okay, I pick 2, right?
Yeah.
Okay, so now find the elements which are smaller than 2.
1.
1, okay? You find the 1, yes? Okay, 1. Find the elements which are bigger than 2.
3, 5, 6, babe.
3, 5, 6. Or maybe, yeah, 3, 5, 6, or maybe in the order, yeah, 5, 6, which is 5, 6, 3, yeah. And find the number, maybe I put a one more 0 here, okay? So that will become 0, 1, okay? Yeah? And if I put another 2 here, okay? Yeah? So and how many 2s are there? There are 2, right?
Yeah.
2, so 2, 2. So now we got the smaller part, the equal part, and the bigger part. Eh?
Yeah.
And the answer is to add at least calling this self, solving this using the QuickSort, and solving this using the QuickSort, and then put this together. So this QuickSort will become 0, 1, yeah, if it's sorted. And this is 2, 2, right? And then this one, after sorted, you can pick any number from here again, like 3, yeah? And then put a smaller one before 3, bigger one after 3, yeah? And then this become what? 3, 5, 6. So you see, after sorting, and I put all the pieces together. Do you see it? Now it's in sorted. Do you understand? So the how it works is that I pick a number, yeah, and I separate this into 3 bits. The one which are smaller, strictly smaller, the one which are equal, and the one which is bigger. Yes?
Yes.
We know this small big equal is in the middle, but this may not be in order, right? Then we calling itself recursively. Remember recursion?
Yeah.
We call the recursive quicksort function to solve these 2 parts. Am I right?
Yeah.
Okay. So now, can you tell me how should I pick this number? I want to pick the number that as the smaller part and the bigger parts are as equal, right? As many as equal, right?
Yeah.
Do you understand? If I pick a number which is 0, then what happens? If you pick a number 0, then there's no number smaller than 0, right?
Yeah.
Then so this bit will be nothing,
Yeah.
right? And then all the elements are on the right hand side. This is not efficient, right? Every time you just sort one element, that's very slow. But these, every time I partition it into 3 parts, yeah. So it's it's quicker. So I want to pick a pivot number, which we call this pivot, yeah? Pivot number.
Do you mean like this? Pivot.
Yeah, you can, one strategy, you can pick a pivot number, which is the random. Just pick any random, yeah? Or you can pick the one which is in the medium. You remember in the medium? Remember we talk about the medium, yeah? Like 1, 2, 2, 1, 2, 3, 4. Eric, 1, 2, 3, 4, what's the medium? What the medium is these two divided by 2, yeah? So 2.5, but there's no medium, but it's very close to medium, so we can pick 2 or 3, right? But this requires another processing, so normally it's not very practical. So we just pick the random number, right? Okay, so now I'm going to implement this QuickSort, okay? So can you help me if you can, okay? Define QuickSort, let's call it numbers, okay? So now what do we check? We need to check if, first of all, if the length of the, if the size of the number we want to sort, if it's smaller than or equal than 1, what do we do? If it's just one number or if it's nothing, what do we do? We just return it, right? If it's a number, it's already sorted. If one number is already sorted, right? Yes?
Yes.
So return what?
N.
N, because the size is smaller than 1, then we return 1. Okay? Now we need to find the parts which is the smaller, bigger, or equal, right? So we have three bits. Now, we first of all find the number, or pivot number. So pivot, we choose a pivot. Don't do that, nobody will see it. Pivot number, we can pick the first one, last one, or the random one, yeah? If you want to pick the first one, it's N0, right?
Yes.
Yeah? But if you want to pick a random one, I told you, I pick a random one, which is random, and then you can say choice. Okay, this is interesting. Choice, N. So what does it mean is that given a list of choice, N, Eric?
Yes.
And it will randomly give me 1. Okay, just one random number, okay? Yeah? Okay, so now I want to have 3 parts, equal part, yeah? And then smaller part. And then bigger part, okay? Yes? Yes, Eric?
Yes.
Okay, now we need to loop in this N, right? For I in N. Yes?
Yes.
And then what should we do now? If I is equals to pivot,
Equal pivot.
then we push this pivot, append.
Append.
Append equals append I. Else if, look, else if, we can short as else if, okay? Else if, yeah? Else if I is bigger than pivot, then what's that? Bigger, yeah? Bigger the append I. And can you tell me what's next? Else, right?
Yeah.
Smaller, yeah? Append I, right? Yes?
Yes.
Now we have the equal part, smaller and bigger part. Now the last bit. So how can we do this? The last bit, okay? The last bit, return. Calling the self. Eric, look, QuickSort, return what? QuickSort. Smaller, right? Plus equal, right? We don't need to sort the equal, right? Because it's already equal, right?
Yeah.
Because if there are 3 2s, and then we don't need to sort it because it's already in order, right? And plus QuickSort. What should I do here? Smaller, equal, and what's this? What's here? We need to sort.
Bigger.
Bigger, yeah. You see, this is recursively sorting the smaller parts and the bigger parts. Am I right? Yes. Look, this is a bit. Eric, look. For I in N, we're looping each number in a list. If it's equal, look. If it's equal to pivot, then we push it to the equal. If it's bigger than pivot, we push it into the bigger. If it's else, it should be smaller, right? It pushes to the smaller. And when you're calling the recursively, QuickSort, the smaller part plus equal plus the plus QuickSort, the bigger part. And now look at this one. We can replace this bit. Yeah, this bit is we can replace this bit by using a simple syntax here. We can do this. Look. Okay, here. Yeah. I'm going to write this, and then you can tell me what should I do. Write similarly. Okay, equal x, any number x for x. What's x for x in n? Yeah, the x now is x, right? But what is x? X is in n. Every number in n, right? If x equals pivot. Okay. So what should I do the smaller here? X for x in n if x smaller than pivot. Okay? And what's bigger the part here? X for x in n
if x bigger than the pivot.
Okay, this is the same thing as this, yeah? And we don't need this. And then return QuickSort smaller plus equal plus bigger, right? Yes? Do you understand it?
They do have to put.
QuickSort.
Do you have to do a new line here?
No new line. I just don't have enough space, so I put it
So all of this is
in one line. Return QuickSort smaller part plus the equal part plus the bigger part. This is calling the smaller part every time. So what it does is look 3 3 2 1 5. Okay. So for example, if I choose the pivot 3, so what happen is that I have this 3 3.
It will be 303,
No.
32, and 15.
No, now 2 is on the left hand side, yeah? And 1 5, for example, like if I say 6 5, okay, it's on the other side, 6 5. So this is sorted, yeah? This is here, yeah? 2 is this part, smaller part. 6 5 is this part. 6 5 is not in order, so I call itself to divide and conquer, yeah? So I solve this problem, I calling the same algorithm to solve the smaller parts, which is 6 5. Do you get it? And after calling that, it will be in 5 6. Then I put it together, that will be 2 3 3 5 6. Do you get it? Now it's in all insorted. Do you get it?
Yeah.
Yeah, so the algorithm complexity for this one, can you make a guess? It's a bit difficult. Can you make a guess? Is it O(n)? Is it O(n) log n? Or is it O(n) squared? Which one? Pick one. Just guess. Just guess. Which one? Which one? Don't worry. Don't worry. If you make a mistake, just pick one, and I tell you if it's right or not. 1 in 3, the chance.
What do you mean?
There are 3 choices. Just tell me which one.
Oh, I don't get it.
The complexity. I mean, how many times the computer, if there are n elements in the array, how many times the computer, how much time the computer needs to spend on sorting?
3?
What 3? I mean, this if it's n elements, how much time the computer needs to spend? There are 3 parts. I mean, calling if there are n elements, how many times? Does it only scan one time, once, like an element, or does it need to scan multiple times? You're not sure? That's fine. You're not sure.
Wait.
You want to guess?
If it scans multiple times.
Yeah. So definitely not this one, right?
Yeah.
Okay. So is it this one? Yeah.
Probably.
Okay. Yeah. This is practically is O(n) log n, but only if you pick the pivot correctly. Remember what I told you. If we always pick the smallest one or largest one, yeah, then the complexity will be O(n) squared, right? Do you get it?
Yeah.
Because every time you just sort one element, right? And then you need n iterations, for each. You saw it takes on to solve one element, and you need to solve n elements, so that will be n squared, right? Yeah. But if you pick the pivot very cleverly, if you pick something in the middle, you always separate into half, right? Remember the binary search, yeah? Very similar, yeah? Remember binary search? Every time you cut in half, yeah? And then that will be log n, right? So that will be n log n, okay?
Yes.
Yeah, I come back to this in the future. Don't worry if you don't get it, but this is a very important algorithm, okay? Okay, say bye bye to the people.
Bye.
Okay,
Bye
bye bye.